All right, day 3 of mirrors. All right, so we are going to be learning about convex mirrors. So Miss Cantrell, she showed one of her flat mirrors where the angle of incidence equals the angle of reflection. And then concave mirrors with Coach Mokler. She should have went over concave, so the ones like looks like satellite dishes. And she should have went over and introduced a lot of the formulas and talked about ray diagrams and all the different rays in order to make that happen. Okay, in order to predict what an image is going to look like. Okay, so she should have talked about the concave, so like the inside of the mirror. Okay, so notice right now you're upside down. She should have talked about how why you're upside down, all that good stuff. You get really close, you get magnified. Okay, so what I'm going to talk about is the flip side, the back side of this. Okay, so you can kind of see everything in there. Right now you see my laptop, okay, with me talking in my laptop. There's some things you're going to notice about the laptop. Notice that it is upright, okay? All of our convex mirrors are always going to be upright images, okay? You'll never have a flipped upside down one. I can do whatever I want with this spoon. Notice that the image will always be upright or erect, whichever word you want to say, whatever that we've been going over, okay? Also, another thing you're going to notice is that the images actually get smaller. Okay, so if this was a plane mirror, you would see my laptop basically the same size and the same distance away from that plane mirror. But because we are talking about a convex mirror, this outer curve, okay, bulging out toward the object, okay, it's actually going to make it a smaller image. Okay, so your image is going to be upright, but it's also going to be reduced in size. Okay, so what are some, when we think about this, how could this be helpful? Okay, other than, making a spoon where you could eat, and it's the backside of a spoon. Okay, so a couple real world examples that I have are security mirrors. Okay, if you go into a store, I think our library has one, our ISS has one, ISS room at school has one as well. Okay, these security mirrors, since everything is made a little smaller, you can actually see more stuff because it's smaller, so everything's squished in. You actually can see more things around because you have light reflecting from these far corners in those different directions to be able to get that image, that light image to come back to your eyes from a different angle. So you can see more things. So security, it's really good. You can help see around, corners. You can see just what people are doing. Okay, if you ever go to Walmart or something like that, look up. You'll see them a lot. Okay, another thing is that's very close to home to what we know about. You can go outside, go to your car, go to your passenger side, and look at the mirror. Okay, so when you drive your car, you actually have your 3 different mirrors. You have your rear view mirror, that's a plane mirror. You have the mirror on your driver's side, also a plane mirror. Okay, everything you see is correct. Okay, but then if you have the passenger side and you also see it has little notes on it, okay, that's actually going to be a convex mirror. And on that little writing, it says objects in mirror may appear or are larger than what they appear. Okay, so I'm going to say it again. So objects in mirror are larger in real life than what they're appearing to be on the mirror. Because again, it's a mirror like this. It's shrinking those cars that are in your blind spot. Okay, it's shrinking everything around so you have a wider view. Okay, can I understand? So you have a wider view. So if I show everything smaller, I can show you more stuff. Okay, that's your benefits of having this convex mirror. Okay, so some things you need to talk about, again, is your ray diagrams. Okay, we're going to go over how to draw those with your parallel ray, your focal ray, your center ray. Okay, I think there's one more. Gray, no, that's it. Okay, so you have those 3. And then we'll talk about the mathematical side. I'll work one math problem with you, and then we'll have some practice problems here at the end. Okay, so let's get on to the ray diagrams. Give me a second to get set up. All right, so for ray diagrams, I just took a blank sheet of computer paper. I'm going to sit and actually draw one out so y'all can see how it kind of works out. So I'm going to start off with just my midline. All right, so there's my midline. I have a little blue solo cup here, and I'm going to use that to represent my convex mirror that I have here. Okay, so I just did a line. There's my convex mirror. Okay, so if we're looking at this in like a spoon, okay, it'll be something similar to this. This is the part that bulges out. This is the concave part that bulges in. Okay, so remember on our convex mirrors, it's just like the back side of a concave mirror. Okay, so same idea here. They're always going to have a focal. So if I was to shine light onto this side, okay, we know that light is already going to converge into a single spot. It's a concave mirror. Okay, so we learned last time. So if I was to shine a light beam right here, it would concave or converge towards the inside. Now, if I was to do that with a lot of rays, they're all going to converge at one single spot. Okay, and wherever it converges to, that is your focal. Okay, so same idea. We have our focal. All right, so our object is going to be somewhere over here because, again, we're talking about the backside of the spoon, whereas it's converging, something looking into it, something being shown in front of it. Okay, so we're going to put our object. Let's go ahead and measure it out because this will help our math later. Okay, so we're going to put our object, let's go 10 centimeters away. Okay, and let's make it a 2 centimeter high object. Just to keep it easy and that we can draw. Okay, so 2 centimeter object. And there's our arrow representing our object. Okay, so yes, and like me, I'm trying to draw upside down again, so give me credit here. It's working out pretty well. All right, so with our ray diagrams, we have 3 rays that we talk about. Okay, we have our parallel ray. Okay, I also call it the P ray. So I'm going to write right here the P ray. Okay. All right, so the P ray, the parallel ray, well, it's the parallel ray. First thing it does is run parallel. Okay, so this one's going to run. We're going to go parallel with our midline from the top of the object to the mirror. Okay, top of the object to the mirror. Okay, and then our parallel ray, just like it does in a concave, okay, goes from parallel to, through the focal. Okay, so we're going to go ahead and line up with this focal over here and line it up with our ray there. Okay, obviously on a mirror, what's light going to do? Light's not actually going to go through the mirror, right? We're going to see it in real life as this ray that goes this direction. It bounces off. Okay, but if we actually want to actually come up with an image and for our rays or our lines to actually intersect all these rays in order to have this image toward our object, okay, then we have to do something because otherwise all these rays are just going to go off on their own. They're going to diverge, not converge. Okay, so what we have to do is we have to trace this parallel ray back through the focal. Okay, so parallel ray goes parallel till it hits the mirror, bounces, and goes through the focal. Okay, which then leads us to our focal ray. I don't know which markers is good here. We're going to go with this one. Okay, so now we have our focal ray. Okay, our F ray. Okay, well, you got it. It's called focal ray. So it's going to aim from the top of the object towards the focal. Okay, top of the object towards the focal. So we're going to trace it until it hits the mirror. Okay, so that's our start right here. Okay, then the focal ray always, once it hits the mirror, then it bounces off parallel. So it does opposite of the parallel ray. Okay, and if it was to bounce back, because it's a mirror, it's going to reflect back that direction toward our object. And again, we want all of our rays to cross in order to create this image. So we trace back behind the mirror. Okay, so that one is our focal ray. Okay, and then we have the very, very last one. The last one, not really have, oh yeah, I guess that's a different color. Okay, we have our C ray. Oh, this marker's been used a few times here. Okay, C ray. Center ray does something very simple. Top of the object to where the midline and the mirror hit. Okay, the center of the mirror, per se. Okay, so you go from the top of the object down to here. Okay, and at that moment, this little spot right here kind of works as a plane mirror, flat mirror, where this would be our angle of incidence, and we know that our angle of incidence must equal our angle of reflection. Okay, so we're going to have it bounce back this direction. So it hits angle of incidence and angle of reflection be equal. Another true, like a little cheat here. If you can line it up, you see about how high the image is here. You should have about that same gap on the other side. So you have the right angle. Okay. And again, we're going to trace back behind. So here we go. Here we go. All right, so those are our three rays. Okay, we have our parallel ray, which goes parallel, then down to the focal. We have our focal ray, which goes towards the focal, then bounces back parallel. And then we have our center ray that goes towards the center of the mirror and then bounces out at the same angle of incidence and angle of reflection. Right? And you'll notice that we have a nice intersection of all of our traced back rays. Right there. Okay, so from our midline, we're going to draw a line up. Okay, and there is our image, our predicted image. Okay, so with a 2 centimeter tall object that is placed 10 centimeters away from the mirror, okay, what we're going to see is we're going to see an upright image. Remember, it's like the spoon. Okay, you have an upright image. And notice that this was 2 centimeters. If we measure this one out now, you would get roughly 0.8 of a centimeter, roughly. Okay, so reduced. So we have a reduced erect or upright. Again, I'm writing upside down and backwards. Okay. And then the question is this going to be a real or virtual image? Okay, so I want to bring back up here for this. So real and virtual, okay? So hopefully we've already kind of talked about it in the previous. So remember that real is whenever all the light rays are actually being converged or something or in front of the mirror. All your virtual are the ones that are, when they meet on the back side or the other side. You had to trace back, in other words. Okay, anytime you have to trace back, it is going to be a virtual image. Okay, so all your convex mirrors, very, very simple. There's no if, ands, or buts. There's no worry about where it's on the focal. Doesn't matter where I put this object. 50 feet away, really, really close to it, doesn't matter. You will always get a reduced, erect or upright, and virtual image. Okay, so that is our ray diagram. All right, so we had a ray diagram, so let's talk about the math side of it, okay? So here I just have this pulled up so that way we can do. We're still going to be going off of the same mirror that we did. We're going to be using the same these equations, okay, that we did last time. I'm going to type them up here in a second. All right, so we have the mirror equation, which is 1 over the focal is equal to 1 divided by 1 over the di plus, I think it's do and then di doesn't really matter, it's just adding, but plus 1 over di, distance of the image, okay? So we're going to use the same one that we did here, okay, that I have drawn. Ignore my little scratches on there, okay? So what we did, so since this is a convex mirror, okay, so what do we notice about the focal? Is the focal here on the same side as the object? No, it's not, okay? So with that said, our focal here on our concave are always a positive focal, but since it's over here on the other side, it's actually going to be a negative focal. Okay, so on convex lenses, you just have to remember that's going to be a negative focal because it's on the other side. Okay, so 1 divided, so I went ahead and measured out my focal here. I took my meter stick, or my little ruler that I have here, and I just measured from the mirror to the focal. Okay, it was roughly 3.6 centimeters. Okay, so 3.6 is equal to 1 divided by the distance of the object, which I'd placed the object at 10 centimeters away. Okay, plus 1 over di, the distance of the image. Okay, so on here, whenever I measured it out, we got roughly 3.6. So hopefully mathematically, sorry, not 3.6. That was my focal. For here, for the distance of the image, I got roughly like 2.5. Okay, so mathematically, hopefully we get about 2.5, because that's what my drawing showed. So my ray diagram showed. Okay, I don't like fractions, so I'm going to get rid of all the fractions. Oh, sorry, I forgot to make that a negative 0.6. I just talked about the negative focal. Okay, so it's really easy to forget. Try not to. Okay, make yourself a note if you have to. All right, so I get 0.28. Okay, then it's a negative 0.28. I'm going to do 1 divided by negative 3.6 equals 1 divided by 10 is 0.1. Okay, plus 1 divided by di still. Okay, mathematically, I'm going to take 0.1 and I'm going to subtract 0.1 from both sides. So minus 0.1, I'm going to say over here minus 0.1 to get rid of that, which leaves me with a negative 0.38. There's a negative minus a negative, okay? Just makes a bigger negative. Okay, and this would be canceled out. 0.1 minus 0.1 inside of 1 divided by di. Okay, now to get di out, I need to times both sides by di. Because it's on the bottom, whatever's on the bottom, get out from on the bottom. Okay, so then those two would end up canceling out on that side. Okay, which leaves me with di times negative 0.38 equals 1. So I divide both sides by negative 0.38. Over here, I'd still divide by negative 0.38. Okay, so then on my calculator, I say 1 divided by negative 0.38, and I get an answer. Di will be equal to a negative. Again, notice where it is. It's located on the back side of the mirror. Okay, back side of the mirror, our image over here. Okay, so negative. I get a negative 2.63 centimeters, which is really close to that 2.5 that I roughly measured. It was actually probably closer to 2.6. Yep. Okay. Look good. So now let's do the magnification. So we already know since it's a convex mirror, it's going to be reduced. We already know. Okay, but the mathematical side of it. Okay. So we have magnification equals height image divided by height of the object, which is also equal to negative distance of the image divided by distance of the object. Okay, so we can do the heights. Okay, we could do distances or we could do heights. Doesn't really matter. Okay, so let's see. Let's go ahead. We have the two distances. We just solved for distance. Okay, so let's do our magnification ratio. So we have negative distance of the image. The image that we just solved for was a negative 2.63. Well, taking a negative of a negative, okay, that's going to give us a positive 2.63 divided by our distance of the object, which was 10 centimeters. That gives us a magnification ratio of 2.63 divided by 10, 0.26. Let me say, sorry, 0.26. 3, if I want to say exactly what my phone says. Okay, so obviously that means, so it's close to 0.25, so that means it's about a quarter of the size. Okay, if we want to know the exact size of it, that's fine. We could do magnification equals image or height over object height. Okay, so we plug this 0.263 in for our m. And our image height, that's what we're solving for, divided by our object height, I did a 2 centimeter high. Okay. So I'm going to say 2, since it's divided by 2, I'm going to say times 2. So I'm going to say 0.263 times 2, 0.5 0.526 centimeters should be, oh, not JI, our height of the image. Okay, so let's see how we did here. I'm going to sit here and I'm going to measure. And that is pretty close to 0.5 centimeters just by going off my ray diagram. Okay, so that's the math side of it. Okay, if you have any questions, please feel free to email me. Okay, Bradshaw J. You can also email your teachers as well. Hope this helps. And yeah, pay attention whenever you go to your car next time, and you'll see a convex mirror on that passenger side. All right, see you later.